Okay, I'll give you some time to work on this. So the two questions you're going to work on, and I'll leave them up while you're working on it, is a question that involves forces, and again, dealing with forces in equilibrium, and then another question dealing with velocity. Okay, now number 2 is one of those questions where, you know, in the end, you probably do save yourself a bit of time working with it using components. Number 1, I really don't know that there's any time saving there. So like I said, I'm not going to solve it using components, but number 2 might be one that save you a little bit of time. But again, you might want to solve it using sort of non-right angle trigonometry to give yourself a bit of a challenge. Okay, so I'm going to give you, say, about 8 minutes to work on these 2 questions, and then we'll come back and take them up. And as usual, you can send me I'm going to get started here. So vectors lesson 5. So if you're watching this later on video, you want to take some time to do the first 2 questions. And we'll take those up now. Okay. So this question here, in fact, let's just look at the whole solution. Okay. Again, you'll notice that I do what I did with that hanging object question is I start with a diagram of the situation just so I understand what's going on. So here I've got my swing, it's pulled back 1.5 meters. They were very clear that that's a horizontal distance. Okay, and then from there I've got my 3 forces acting on the object, and because the child is being held at that point, it means at that particular moment in time, not moving, so we know that the net force is 0. Okay, now this is where you have to be careful because these are measures of length. Okay, they don't really tell us necessarily anything about the forces. The only force we know for sure, because of we know the mass of the child. It looks like we're assuming the tire has no mass. Again, math course, we tend to do those kinds of things, so we'll assume all the mass is within the child. Okay, so from there, we only have one force. So when I draw my force diagram, you know, I would have started with my easier one, the one going straight down. Then I know the person is pulling horizontally. So that's the force of the person pulling on the swing. And then, of course, there's the tension in the rope or the string that's attached to the tire. Okay. So do you need to include the free body diagram? No, not necessarily. It's just, it's a good idea. Again, it depends on how much facility you have with these questions. Okay, some people are perfectly fine going to this one here, and this is a fairly easy example. You know, maybe the one with the strings. Yeah, with the strings the 2 strings holding up an object, that might be a good idea to actually draw out the diagram. So again, depends on your facility. But if you're solving it using well, in this case here, it still is right angle trigonometry, then I would expect to at least see the force diagram. All right. Whereas somebody solving it by components would probably just draw this diagram and wouldn't be drawing the one on the right. Okay. But in the end, we don't have enough information to solve this, because even though we know it's 90 degrees, we have only one side length. What we need is, you know, either another side length or an angle, and that's where you realize that the angle of the tension, that force, can be found because you have enough information between the length of the rope and the distance that it's been pushed back. Okay, so this represents the angle that the tension makes with the horizontal. So I can, because it's a right angle triangle, I can use right angle trigonometry, solve for the angle, and now that becomes part of my diagram here, and now I do have enough information. So in this case here, I use tan to find the horizontal force and sine to find the hypotenuse force. Okay, so let's take a look at some of the questions that are coming up. So how precise do you like your answers to be? Because for some answers you use 2 decimal places versus 1. I guess if I'm not specifying, just, I would say assume at least one. 2 is probably even nicer. So, I'd probably be more precise in a test. Okay. Next one, would you expect us to draw the vectors in such a way that they form a closed shape? Well, it depends what diagram you're drawing. If you're drawing the freed up body diagram, well, that's not going to be the case here. If you're summing up, the 3 vectors, then yes, they have to add up to 0. And so, or that they add to 0, I mean. Yeah, exactly. They add up to 0, so it must be a closed triangle. If it was 3 forces acting on the object and it was producing some non-zero net force, then it wouldn't be a closed triangle. So I'm not sure if I answered that question. Let me know. And here, do we need to include the angle on the force of tension, or is it just the magnitude? So yeah, so here you can just give the magnitude when you're talking about the tension, because essentially the direction is whatever direction the string is in. Okay, so it's sort of it's incorporated that whatever direction the string is in, that's going to be the direction of the force. So you just have to provide the magnitude. Okay. I guess in this case here, is it same for the horizontal force? Yeah, same thing, because it was already clearly given the direction was given in the question, that it was being pushed backwards horizontally. Okay. All right. So again, fairly typical type of question where you're working with something that's in equilibrium. Let's take a look at the next question. Okay. And here, you got a few things going on. So you have 2 velocities that are going to be summing up to give a ground velocity or a resultant velocity. You have the current, which is eastward, and then the water velocity, in other words, the speed at which the boat is actually, the velocity that it's actually, that I guess the rower is pointing it at. Okay. So they want us to know how long it'll take to reach the North Shore and how far downstream the boat will have traveled. Okay. So if I start with that first part, okay, so the first thing I do is, and again, I'm not doing this via components. The first thing I do is I determine the resultant velocity. So I'm starting on the South Shore. There's my velocity in still water, but of course, they're also affected by the current, which is going directly east, and then here's my resultant. Okay, now of course this 40 degrees that's given is not inside the triangle, but I can use the fact that the east-west river, so this line here goes east-west, and then this line here in that vector is going towards the east, so I've got parallel lines, so it means the obtuse angle and the acute angle are going to be supplementary to each other. So that's how I get the 140, and then from there I solve for my magnitude and direction. Okay, and again, as usual, you see me not even thinking about sine law, even thinking about whether I need to worry about the ambiguous case, because cosine law works. And once you become adept at using cosine law, it's not like it's that much more time to calculate it. Okay. But of course, this is not what they're asking for. They're asking for how long it takes to reach the North Shore and how far downstream. Now, you'll notice that in that, I'm going to do the second one first. When I do the how far downstream, I'm actually going to, oop, I don't want to show that. That's the, okay, I'll just show the whole thing. There you go. How far downstream? I use the fact that whatever distance it travels along the water to go across, it's going to be at the same angle as the velocity. And I already know one side of this triangle. So if this is where they start on the North Shore, that's where they are in the South Shore. That's the direction of motion. So that's the distance they travel in the water. But what I'm looking for is how far downstream. So I'm looking for this length here. I know the 2. Now, how did I get this angle of 58.9? Well, I said this angle here is 40. Okay, meaning that if I draw a little line there, what remains is 50. So it's just going to be 50 plus this angle theta that I found from the previous question. Okay, so that's how I got this angle of 58.9. So I'm able to calculate the distance just using nice, easy trigonometry. Okay, now in order to determine, okay, so we still expect to calculate the direction of the boat's motion? The question is, no. So for example, you'll notice I didn't calculate the direction here from, say, east. Why? Because that wasn't part of the problem. If they had asked me to determine the resultant velocity, then I would have found this angle here in order to, or I could have used this angle and said north 58.9 degrees east. But you're right that it was never asked in the question, which is why I don't bother giving it. So I'm just answering what they're asking. Okay, now how did I find the time? Well, I said, let me find this distance that it travels, and remember that I know its speed. And again, assuming that it's traveling at a constant speed, which is, you know, what, even though they didn't specifically tell us that, that's what we're going to assume here. I can just use my relationship between time, distance, and speed. Okay, so I already knew the speed. That's just the magnitude of the velocity function. I calculated the total distance traveled in the water because I already have these two sides. So I use Pythagoras, and then from there I just did distance divided by speed to get the amount of time it takes to travel across. Okay, now I suspect that if you did this using components, you would have probably used something a little different here to do that, but either way, you should have gotten to a very similar answer. If it was a little different, it might just be because different types of approximations that you made. All right. So again, these are, you know, sort of, I would say, two very typical types of questions that you can get in terms of thinking about vectors in terms of forces and velocities. Likely won't get too much more difficult than the ones that we've seen. There are a couple of nice little questions in the homework that you know, are slightly more challenging, but in terms of application questions, this is pretty much the type of thing you're going to get. Okay, and yes, hopefully I won't have to repeat this again. If you solve all these things using components, that is 100% okay. All right, any last minute questions on either of these? Okay. So I would say if you didn't take physics last year, I just stick with sort of regular old trigonometry. I don't really see a point in learning a whole new way of doing things. Whereas if you did do this type of stuff last year, you're welcome to continue that. Okay, anything else? All right. So let's go back to old Broccoli Bear who wants to, oh, wait, let me get that here. There we go. So we've got Broccoli Bear here who now decides not only does he want to just go around on the ground, he wants to, oh, where did Broccoli Bear go? Well, Broccoli Bear clearly wants to expand his horizons, and oh, hey, look, there's Broccoli Bear. So Broccoli Bear now isn't just living in a two-dimensional world where he can travel anywhere along 2D plane. Broccoli Bear can now go anywhere. Okay, so the question is, how do we describe things like position? How do we describe motion, direction of motion, if we're talking about things like velocity, or if force is applied? How do we describe that? Okay, so hopefully we can see that north, south, east, west isn't going to do the trick, because, you know, north, south, east, west, I have to at some point, you know, give it some height. Now, there in fact is a way to do something similar. Okay, and in fact, astronomers still use this in terms of direction. Is say you just say that's north. Okay, well, what you do is you say, well, let me take an angle from north, go counterclockwise, and that gives me an angle. And then from there, I can give an angle of elevation. There you go. There's my angle towards Broccoli Bear. So you notice that's two pieces of information. And if you want the position, then the distance between where you are and where Broccoli Bear is that third piece of information. So notice how we need three pieces of information to describe something like position, two angles, and a distance. And that's a perfectly good way. Now, very often when you're dealing with astronomy, you only really care about direction, okay? You're not actually thinking about how far these, stars would be out in the sky. So they still use azimuth and ascension. I think that's what it is, azimuth and ascension. Now, I'm not going to try to draw this out, but I'm hoping you can see that solving the problems that we've been solving is going to start getting pretty complex if we try to describe position and direction using two angles and a distance, okay? So the idea is to come up with a whole other way of describing 3D space other than that one there. That sounds a little more like our north, south, east, west from 2 dimensions, okay? And I think a lot of you probably know what's coming up. And what we do is we use a Cartesian system, okay? So in the same way that in 2D, you could have an a y-axis and an x-axis, and you define positions by giving, an x value and a y value, okay? Well, we can do the same thing in 3D, where we have 3 axes, where, say a position, say a point in 3D is given by an x component in that direction, then a y component in the y direction, and then a z component upwards, okay? So this is what we refer to as R3, or 3 space, okay? The Cartesian plane, when you're just sticking onto a 2D space, that's 2D or R2, or 2 space, okay? So in terms of positioning things, we now have this new way of looking at things. Now, of course, we can't go around holding up a 3D Cartesian space, okay? So we're going to have to find, yeah, we're getting there, Kieran, okay? We have to find a way to represent this on a 2-dimensional piece of paper. Now, before we do that, let's talk about how I've positioned these X, Y's, and Z's. Why isn't, X going in that direction? Why is it in this direction? Or could it be one or the other? Well, it's not just ad hoc, okay? Well, so we got to figure out, it turns out it was the right-hand rule. So the way this works, okay, and we'll see this in 3D, and then we'll see when we try to draw it in 2D, okay, is that you start off with your fingers here, and you start off by pointing them wherever you want your x-axis to be. Okay, I'm going to try to position this so you can see it. So wherever your x-axis is, that's where you point your fingers. Then you curl them inward, and then that gives you where the y-axis has to be. And then you just lift your thumb, and that gives you your z direction. Okay, so if I decide I want the x pointing there, well, let's see if this still works. I place my fingers in the x direction. There you go. Y direction, and going upwards is my z, like before. Okay, so this is how we determine the location of these axes. All right, so let's go back and take a look at how I'm going to represent this on a 2D surface, okay? And what you'll notice is, well, it looks like there's a 90-degree angle between the z-axis and the y-axis, but what you have to imagine, and this is why you see this slantedness, is that what I'm trying to do here is I'm trying to create a sense of depth, a sense of perception. So what you have to imagine is that there's a right angle between the z-axis and the y-axis, that there's a right angle, okay, that this here represents a right angle between the x-axis and the y-axis. All right. So essentially, what this represents is, you have to imagine the z and y are on your sheet of paper, and the x-axis is coming out of the, smart board here. It's coming out of the page. Okay, and we put this slanted. We draw it in a slanted way to give this sense of perception. Okay, so the way in which we determine a point. Okay, so on the x-axis, which side is positive and negative? Oh yeah, so the one that's coming out is going to be the positive x-axis, and the one that this represents going into the page is going to be the negative side. Okay, for z and y, it's a little more traditional because, positive z, negative z, positive y, negative y. Here, that's why we place the little x here to represent that this is the positive x-axis, and then that would be the negative x-axis. Okay, so if I want to represent a point, say I want to represent the point 2, 1, 4, well, what would I do? I would go 1, 2 along the x-axis. Now, this is where I have to be careful, because when I go along the y-axis, I have to move parallel to the y-axis. So I go 1, 2. And then if I want to go up, well, I move parallel to the z-axis, 2, 3, 4, 5. Now you might sort of say, well, wait a minute, 5 is up there. But you have to remember that I'm trying to create this sense of perspective, this sense of depth. And I'm hoping you're seeing that this is not necessarily very easy to do. Okay, so we use a little trick to make it a little more, a little clearer when we're trying to represent this 3D world on a 2D piece of paper. And it's this idea of using a rectangular prism. Okay, this really helps to give you that sense of perspective. So here, what did we do? We went 6 units in the x direction. So you'll notice here, instead of an ordered pair, we have an ordered triple. 6 units in the x direction, 2 units in the y direction, notice parallel to the y-axis, and then 4 units upwards. Okay, and there's your point. Now, if you want to think of it in terms of, individual components, there's your x, there's your y, and there's your z. But you draw this rectangular prism to produce this sort of sense of perspective. Okay? So there's 2 things that I've got some, some bad news and some good news. The bad news is that this is not the easiest thing to draw. The good news is that I'm pretty sure we can figure out ways to work in 3D that's not going to require you to have to draw things out particularly precisely. Okay. Now, when I teach grade 10 and I do analytic geometry in grade 10, I try to encourage kids not to draw Cartesian planes. Okay, it's just to draw diagrams that people use as a guide to solve the problem without being forced to work on a Cartesian plane. The reason why I do that is that once you get to 3D, you don't want to have to try to draw exact diagrams. All right. So let's take a quick look at the first part of the notes. Let me get those here. There we go. Okay, so again, we call it 3-space, Cartesian 3-space, can be denoted R3. Okay, so it's not an actual exponent, it's just representing that there's 3 axes. Okay, we're going to try to make this so it looks as much as possible as to how we define things in 2D. So instead of an ordered pair, we have an ordered triple. Okay, so it has to be in that order. The first one represents an x value, second a y, third a z. Okay, and of course, all axes are perpendicular with each other. Okay, there's this right-handed system. So this x-axis comes out of the page. You curl your fingers, gives you your y-axis, and then the z-axis is going upwards. Okay, and if you look at what they've drawn here, if you take the portion of the graph that only contains values in the x and y direction where z is 0, well, essentially what you have is your good old xy plane that you know and love. But of course, you also have an xz plane where y is always equal to 0 and only values in the x and z directions. And then you've got a yz plane where the x's are 0. Okay? And the way in which we plot a point, again, you're going to try to use this whole rectangular prism idea. Okay? So if we go back to our lesson sheet, okay, what I want you to do now is I want you to give a try on drawing these points. Okay, so try to, again, make sure you're following things in a parallel way. So when you go to the x, y would be somewhere in this direction parallel to the y-axis, and then up and down parallel to the z-axis. Okay, this one will be a little more interesting because you got some negative values. All right, so let's start by drawing these out. So I'll give you, so again, I'm not going to ask you to draw tons of these, but it is good to force yourself to do a couple of them. So I'll give you maybe 3 minutes to try to draw these 2 points and try to be, doesn't have to be perfect, but try to be as exact as you can. Okay, so we're back here. Let's take a look at my diagrams. And again, they don't have to be perfect, but just to give you a sense at what I would have done is I would have started 0, 0, and I would have gone in the x direction 2. Then I would have created this, you know, what looks like a parallelogram in the diagram, but really is a rectangle, because I have to remember that these two are representing perpendicular lines. Okay, and then you'll notice here what I did is I measured what 4 units would be, and I went up 4 units above this point here. Remember, this point is supposed to be outside of the page. Okay, I'm representing it again with this angle, the idea of creating the angle to create the perspective. Okay, so this is the mistake that's often made, is people go all the way up to whatever the y value, z value is, which in this case is 4. Well, no, you have to measure the distance of 4, and you're measuring it from this point here. And then from there, I create my rectangular prism. Okay. Now let's take a look at this one here. Again, same thing. I went 2 in the x direction, -2 in the y direction, and then 3 in the z direction. So what I would have done is I would have measured more or less how long this is. There you go. And then I create my rectangular prism. Okay. And what you have to imagine is that this point is below the xy plane. Okay. And to the left of the xz plane. Okay, so the rectangular prism helps you to show that. All right. So again, this is not something, you know, you need to practice a million of. I think I give you a couple in the homework. Just going to say that we forced you to draw a couple of these. But what I want you to keep in mind is our goal is to be able to do all these questions without needing that diagram that was so useful for us back in the previous sections. All right, so any questions on this before we move on? Okay, so do you need to draw the box? I would say you really should, because otherwise, if I were trying to grade something like that, it's very hard. Wherever you draw a point, it's not, I have to do a lot of work to figure out that it's in the right place. So drawing the box kind of means that I'm happy because I can see that you know what you're doing, and you know, much less likely to be to penalize you if you're a little off. Whereas if I have to go through the motions of testing your point and it's off, then you know, I can't be sure if it's because you didn't know what you were doing or you just weren't being precise with it. Okay, so you should be drawing. Like I said, the few times you're ever going to have to do this. All right. So if we're saying that we want to avoid having to rely on the diagrams like we did in the past, at least with, the north, south, east, west questions, then if we're going to come up with a new way of describing vectors in 3D, maybe we can actually just come up with a new way of describing vectors altogether. All right? And this is where I want us to go back to something we saw a while ago. Okay? All right? And I want you to remember when we sort of started talking about numbers as though they were vectors. And how did we describe these numbers? Well, we said, hey, why don't we just think of this number 5 as being the vector from 0 to 5. Okay, and we called this, that was vector 5, which represented the number 5, and then this was vector 3, and we saw that this gave us some inspiration as to how to define addition, the idea of defining the addition as putting them tip to tail. Okay, well, what if we take this idea and move it to 2D? Okay, so instead of describing a vector using north, south, east, west, or describing an angle to another vector, okay, or always having to run an arrow, what if we actually use the fact that we have this Cartesian plane to define vectors? So we have to remember, what are the two things that tell you what a vector is? What are the two pieces of information that define a vector? Magnitude and direction. What is not important in defining what a vector is? There you go, position. So since defining this vector is only about defining its magnitude, so the length of the vector, and the direction where it's pointing, well, I can place this vector anywhere to define it. And so why don't I just choose to place that vector at the origin? So instead of explicitly giving the magnitude of the vector like we were doing before, let's use the fact that it's starting at 0, 0 and ending at some particular point. In this case here, it's ending at the point AB. And guess what we're going to do? We're just going to call this vector the vector AB. Okay. Now, if you remember back when we were talking about interval notation, I told you that at some point, this notation, which of course we know can represent a point, we know it can represent an interval from value A to value B. Well, this is now its third meaning. Whereas this now represents the vector that starts at 0, 0 and ends at the point AB. Okay? Now remember what we said is that vectors can be movable. Guess what we call this vector now that it's not starting at 0, 0? Does anybody want to guess what we call that vector? Yeah, be more precise. That's right. It's still called vector AB. Okay? And that's the beauty of this here, is I use this position to define the vector, okay? But regardless of where I move it on the Cartesian plane, this is still the vector AB. Because when you see this, you assume that the length of the vector is given by the distance from 0, 0 to the point AB, okay? And whatever direction that gives us, okay? So while we're defining this vector by placing it at 0, 0, when we move it around, still the vector AB, all right? So let's say we assume that the scale on this is, 1 unit. So what vector would this be? Tell me what vector this would be if we assume that the scale is 1 on the x and y axes. Who can tell me what we would call that vector? Yeah, what are you missing though? So I have an answer, but I think we might want to, there you go. So this is an ordered pair where the first is always the x value, okay, which in this case here is 5, and then the y value is 3, and don't forget the brackets, okay? So what vector would this be? There you go, 2, 3. Well, wait a minute. What if I move it here? What would that vector be? Still the vector 2, 3. Okay, so while we use the origin to define it, when I move it around, it's still defined in that exact same way. Now you might sort of say, well, okay, was there a point of this since we already have a way of dealing with vectors in 2D? Okay, so the answer might be, well, no, maybe we don't need it. You know, you have a whole system. I don't think you define vectors like this in physics. You had a whole system of defining vectors in physics that worked very well in two-dimensional motion. So in order to switch to this way of defining vectors, it would have to provide some good that's the word I'm looking for. Have to make things a little easier, okay? But definitely one good reason to use this way of defining vectors is because this is how we're going to define vectors in 3D, okay? So if you take this point ABC, okay, and you draw a vector starting at 0, 0, 0 to that point ABC, well, guess what we call that vector? That's just the vector ABC. So instead of just drawing the point, say, 3, 4, 5, we can draw the vector 3, 4, 5. All right? So let's take a look. So this is where we're heading. Okay, this is why we're really defining this, because in 3D, working with things defined with respect to angles would make adding, subtracting them very difficult. All right, whereas this we're going to see is going to allow us to do those calculations much more easily. And in fact, we're going to see that it's going to make life even simpler in 2D. Okay, so let's take a look at the notes before we move on. Actually, no, let me have you do a couple of examples and then we'll take a look at the notes. Okay, so let's go back here. So I want you to represent these vectors, okay? So here in 2D, here in 3D, so you'll be doing something very similar to what we did before. The only difference is you're going to draw the vector starting at 0, 0 and ending at whatever point you get to. Okay, and so here you have somebody saying this is kind of like working with it in terms of components, and the answer is yes, it is. Okay, except these components now, we think of them as lengths along the axes. Okay, so let me give you, these should be pretty easy to draw. These will take a little more time, so let me give you, I think 4 minutes should do it. Okay, folks, so we're back. Let's take a look here at these answers. So here, again, the vector 4, 5. Again, I just give my scale here. So 4, 5. There's my point 4, 5. So the vector 4, 5 just starts at 0, 0 and ends at 4, 5. Negative 3, 5 gets you into the second quadrant. And here, this gets you just right along the y-axis going downward. Okay, now here again, the first thing I do is I draw my little box 1, 2, 4, and then from there it goes from 0, 0 to the opposite corner. Okay, the diagonal. So this vector represents the diagonal of this rectangular prism. Now, I want you to sort of think about one of the things we're going to do tomorrow. Is at some point we're going to have to figure out what the magnitude of a 3D vector is given by, and hopefully you can see that this is something we've actually done before. Okay, and then here I just went, what did I do here? I went to -2, 2, and -3, and there's my vector. Now again, I want you to imagine this arrow there without the box. And you can probably see that, it would be very difficult to tell what vector that is. Now, this is where I want to bring your attention to something even worse. What if I had to draw 3 of these vectors and draw, say, a triangle, 3 vectors in equilibrium? Can you see that doing this, being dependent on the diagram, would just be a total mess, okay? So this is why we should be hoping that there's going to be some nice way of thinking about addition and subtraction and scalar multiplication and all that stuff that's not going to involve being subjected to having to rely on a diagram, okay? So any questions here before I move on? No, so the quiz is, remember, you're writing the same quizzes as those doing the official course. So we're going to be ahead. The quiz will only be, I guess I'll send out an email to tell you what material it covers. It essentially covers the material that's in the assignment that's due Monday. Okay, you'll notice the assignment will not contain a lot of, some of the things that we've done already. All right. So the last thing I'm going to ask you to do, and then we're going to kind of put everything together, look at the notes, is I want you to look at the idea of how we would determine the magnitude, and ideally a formula for the magnitude of a 3D vector, and how would we describe the direction sorry, a 2D vector, yeah, so a 2D vector. So we'll stick to the Cartesian plane. We'll get to 3D tomorrow, okay? But how would you determine the magnitude of a vector AB? And what would be a useful way of describing direction with this vector on the Cartesian plane? Okay, so I'll give you, again, a couple of minutes to think about how you would do that. If you can come up with a formula, even better. Okay, so assume you're dealing with some, random 2D vector. Okay, so you can start by working with, say, 4, 5 or -3, 5, but try to think of a vector AB. What would that give you in terms of finding the magnitude, and how would you describe the direction? Okay, so we're back. So hopefully we can finish this off fairly quickly. So let's take a look here and see if you came up. Good answer here. So I'll use this Cartesian plane. So let's say I take some random vector, and let's start, say, in the first quadrant. Okay, so if this is the vector AB, all right, who's going to tell me how I'm going to determine the magnitude of such a vector? What could I use to determine the magnitude of such a vector? Yeah, good old Pythagoras. Because remember, we're defining this vector as starting from 0, 0, going to the point AB. So I have this right angle triangle where this is my side length here, and this is my side length there. And so if I want the magnitude of the vector AB, well, it's just going to be the square root of the sum of the other two sides, sum of the squares of the other two sides. Now, this is all well and good for something in the first quadrant, but let's say I've got this vector in the third quadrant. Okay, let's assume A and B are positive numbers. Let's say I call this, let's call this -C, -D. Okay, does it make a difference that these are negative numbers in terms of finding the? No, because if I still create this right angle triangle, the length of this side is just going to be, positive C, so kind of negative C, and the length here is just going to be negative D, okay? So that when I apply my Pythagorean principle here, well, what's happening with these two with these two components, they just end up getting squared. So the fact that it's negative c when it gets squared still becomes positive, that it's negative doesn't matter, okay? So what we seem to have is a formula for the magnitude, okay? Now, before I talk about direction, this is where we're kind of seeing the disadvantage of this here. Because when we were working with our other ways of describing vectors, they just gave us the magnitude. I didn't have to calculate it. They told you, no, this is the magnitude, and then they gave you direction. You know, here, I'm going to have to figure out how to describe a direction. So there's definitely something we lose in using this method of describing vectors, is we don't have the magnitude and the direction given explicitly. And that's a big loss. That's in some ways why, you know, certainly in elementary physics, you kind of don't like necessarily using this method of working, because you like to be able to imagine what the direction is, to be able to know exactly what the magnitude is. So the advantages we get from working with this perspective of vectors better be really good to make up for the fact that I have to, you know, calculate the magnitude instead of it being just give it to me directly, okay? So what about direction? We're working on the Cartesian plane. What have we used in the past that might be useful for describing direction? Okay, definitely slope, okay? Anything else? Yeah, unit circle, the idea relation to one of the axes. And that's the one that we take, okay? Because remember here, at some point, we're going to have to bring this up to 3D. And how exactly do we define the slope in 3D? Okay, remember that the slope is a rate of change. It's a rate between two measures. How do we describe the idea of slope in 3D? Okay, in fact, that's, you know, probably what you'll be looking at a lot if you take a third calculus course in university, okay? But dealing with angles, or at least angles to an axis, well, that's something that we will be able to move up to 3D, okay? And anybody want to guess which axis we use? Yeah, not just X. Can we be even more specific? Yeah, may as well go with what we know, you know, the positive x-axis. So here it's nice and easy because you're in the first quadrant. So if you call this angle theta, how are you going to determine that angle? What are you going to use? Yeah, just use tangent. Okay, so you know that theta here is just going to be equal to the inverse tan of, okay, opposite over adjacent, b over a. Okay, nice and simple. Of course, when you start getting to these other quadrants, if you find this angle theta, what are you going to have to do with that angle theta? If you want to describe it from the positive x-axis, there you go. You're going to have to add 180. Okay, if you're in the second quadrant, okay, and you find this angle theta, well, first of all, what can you tell me about this angle theta if I use this formula? Because now my a value is negative. And what kind of answer does inverse tan give you when the input is negative? It's going to be negative, okay? So you'll still do 180 plus theta, except you're adding a negative angle. So it's going to be, you know, that and then minus that angle there. So essentially, you're always going to be using inverse tan of b over a, but depending on what quadrant you're working in, you're going to have to kind of do a little bit of work, possibly, to describe the angle from the positive x-axis. So again, we better be hoping that we're not going to need the angle very often in order to solve these problems, because this now feels like it's getting a little complicated. So again, what I'm hoping is that, you know, when we start adding and subtracting vectors in this form, we're going to get something that's going to allow us to sidestep working with the angles all together. Okay, so let's take a quick look at the notes here. Sorry, this is going a little longer than I anticipated, but let's just take a quick look at the notes here. Okay, so notice here I'm now qualifying this idea of vectors. Thinking of vectors in terms of vectors on a Cartesian plane or Cartesian 3 space is what we refer to as algebraic vectors, okay? As opposed to what we were working before, which was geometric vectors. So geometric vector, we give you the magnitude and direction explicitly. With an algebraic vector, it's given using coordinates on a plane, or as you'll see tomorrow, or see a little later on, 3 space, all right? But what you lose in the process is when you look at this, it's not immediately obvious what the magnitude is or what the direction is. If I get 2, 7, I have to do some work to get to that, okay? Now, you'll notice this alternate notation. They're both acceptable depending on what textbook you look at. Sometimes it'll use the round brackets, sometimes it'll use the square brackets. I'm just going with the round brackets because that's what the textbook uses. So I'd rather not have you see, different ones all the time, but this is a perfectly good notation. And remember that when I define this vector, it's defined as the vector that starts at the origin, which we refer to as O, to some point. So notice here, when it's just a letter that doesn't have an arrow or is not bolded, this is the point AB as opposed to the vector AB, okay? But while I define the vector starting from 0, 0 to a particular point, it remains that vector even if I move it around, okay? And how did we describe the magnitude? Well, the magnitude we saw was just a straightforward application of Pythagoras. And in terms of, the direction, we give it relative to the positive x-axis. You'll use the inverse tan of b over a, but you're going to have to do a little thinking along the way. Depending on what quadrant you're in, you're going to have to decide how to use that angle, okay? And lastly, we then use this perspective of vectors to bring everything up to 3D. Okay, you define the vector u, x, y, z, as being the vector that starts at 0, 0, 0 and ends at, I guess here I have ABC instead of x, y, z. As you can just imagine this is x, y, z, okay? And that represents a vector in 3 space, okay? So what we're going to have to do now is kind of go back and look at how do we operate on vectors now that we're using this different perspective. All right, so that's it for this lesson.